It's your time.
Hello, everybody. Thank you for being here. So today we're going to talk about how to we leverage Ray and vLLM for the GenAI batch prediction at Uber. This presentation prepared by Baojun Liu, that's myself, Bo Ling, and Anant Vyas. We're all software engineers at Uber Michelangelo. Michelangelo is Uber's unified ML platform, so it provides end-to-end machine learning application support from data preparation, feature engineering, model training, evaluation, model deployment for experiment and production, prediction, monitoring, retrain, everything. So in the past few years, actually, Michelangelo have been evolving from XGBoost model to the deep learning model. Since last year, since the GenAI technology emergence, Michelangelo have been actively developing the tools and pipeline to support the GenAI-based applications, so turn into a GenAI platform. So we have a bunch of tools like LangFX is, for example, is a long chain-based tool to actually help the user to easily develop a GenAI-based application. We have the GenAI gateway, basically provide a unified interface to user to call the models, like a third-party large language model from OpenAI, Germany, or it's a self-hosted model. We also have the safeguard and PI detection, basically for the security and privacy. We have a MA Studio provide a UI basically for people to select the model you want to use, prepare the data for RAG application, prompt engineering, and model fine-tuning, monitoring for the performance, safety, cost, everything. So today we talk about batch prediction. So batch prediction is basically use case is if you don't need a real-time application, you don't need a real-time response. If you need that, you probably need to deploy it for endpoint. You can get instant response. But for batch prediction, usually you have a data side. You have a model, either raw model or fine-tuned model. So you run inference and get result and put it into a database or somewhere. So for our use, we use it for offline scoring jobs. Typically, this type of job, we process 1 million to 1 billion rows. It's or we call it a prompt for text generation cases. This case usually take 1,000 to 5,000 input tokens. Output token usually a couple hundred to 1,000 range. That's a typical job we need to handle. So basically, 1 million maybe several million, 50 million. That's we want to finish in daily. That's basically the problem we're trying to resolve here. So give an example how we use it and why we need it. For example, for user store tagging. For example, for Uber we got Uber Eats get daily data. You have a store, for example, restaurant. We can want to tag it. This what kind of restaurant is this? Is it American food, Asian food, all those stuff. We want to do the search. We can pull the search result for a search evaluation and get the quality of searching. We have a document. We want to do document summarization, categorization, labeling. For document, we can do ingestion, get embedding, and save in vector DB. So later we can for retrieval. So basically that's user cases. So just to give some comparison, the batch prediction LM for compared to traditional machine learning is quite some difference. Is for model size is much larger. For example, our traditional machine learning typically is in couple megabytes, but for large language model, it goes to 10 GB, 1,000 GB. For example, the Llama 3.45 GB. Even use IP8, you got 800 GB. The latency-wise, typically we control our data model, ETA model, is less than 10 millisecond latency. But for large language model, it typically can go to seconds. Depends on how many tokens you want. You can do tens of seconds. Throughput, you can handle 100 to 1,000 prediction per second. And for large language model, you can only get a couple prediction per second. For serving, you can use the CPU or use one GPU with not a lot of memory. But for the large language model, typically need multiple GPUs and you need a lot of memories to be able to host the model. In general, the large language model batch prediction was pretty costly compared to the traditional model. Like an example for the mixture 8 times 7B model, you're gonna need two 800 H100 8GB memory to host it. If like a 1 second latency, if you don't have a good batching mechanism, like say you process like one request per second throughput, or typical job we handle like 50 million prompts, you're gonna this many GPU hours. So it's a prohibitive expensive, and you cannot finish basically on time. Certainly you need a distributed system to handle it. So to highlight the challenges, so one is we mentioned the large model size. Basically, you're going to put some resource pressure. One is to save them. Another is you download such large models, so you put some network bandwidth issue, because when you distribute system, you download them concurrently, so basically you need bandwidth, otherwise it's going to take a long time to download them. It's high latency and low throughput. Basically you need to algorithm to optimize it. You need effective batching to increase the throughput, and then you have try to get a good GPU utilization to lower your cost. So serving certainly need distributed system, otherwise you cannot finish basically on time. So you need a GPU serving, you need to be a node level orchestration. You also need in-node kind of tensor parallelization to manage like more than one GPU. So in general, you want a batching system to be scalable, performant, reliable. So scalable, so you can easily do the horizontal scale to handle the large job. Then your performance, so basically you get a good GPU utilization, lower your cost, effective batching. Reliable, so basically you don't actually get the job lost, in the long hours. So here, Ray basically is the good tool to help us here. You can have you easily to scale the job from like one to many. You have a good GPU support to do effective GPU management, either node level or something, or it's a ML tuned, so you have the good granularity and flexibility, so you can user control the function. This is pretty helpful for the large language model because a lot of the implementation is not so standardized. So it's also if your cluster is on the Kubernetes is working pretty well on it. For our system, we are using Kubernetes. We have our unified API and the job controller basically to control how we start to manage a cluster, so we can start to read on it and we can run the prediction. So for GPU, we have A100, we have H100. H100, each node we have 8 GPU, then each have 8 GB memory, then connected by NVLink, so to get a good fast communication. So how do we control the a read job? For the typical flow is you have you start to define your read job spec using YAML file or something. Then you can basically define a read job. Then you create a cluster for control how many nodes you need, how many GPUs or CPUs on it. So once the cluster is ready, you can submit a read job. This can be done with we have the API basically wraps the REST API to manage the read job. Then you can wait the read job to complete and get relog and result. Then you can shut down the cluster. So the read job submission, you can submit a command to the read head. Then basically you have a script located on the read head. Then this script should be capable to actually able to manage the job on the read to basically scale your job from head to worker. Then you can specify where to put the data, where to get the model. You specify the number of worker and GPUs, number implement, how to manage those in this script, by the way. So that's typically how we handle the read job. So the read basically provides some interactive environment. You can use a Jupyter Notebook to actually do the code development and testing. You can also submit a job manually to do testing before you put in the pipeline. So you also have the dashboard to access the log, monitoring the GPU metrics, everything. Here is basically a straightforward implementation. Basically, typically, like for you have like online prediction, you have something set up for inference to one node. So you can use array to actually expand into multi-node. This is a straightforward implementation. The good thing is often you need the online-offline consistency. So basically, you spend for this. For the offline, you got the same result as your offline got the same thing as the online. So basically, each of the reworker array head, you're gonna handle the like working as like an independent node to get the model, get the input, and get the output. So you probably need a leverage array to do some partition, then result aggregation. But every actor like acting like individual, like single node, just like the online for the online-offline consistency. So, so here we can show some quick how we can implement this. You can set up like an actor pool and basically like a number of actors you need, a number of GPU you need. Then you can define the actor call for prediction job. So basically you want to call what you're going to run for each of the actor. This one is something like a scoring, you're going to define it. Then you can trigger it, then you can pull the result to the array head. You can also choose to upload the result in each of the node you want to. This is basically straightforward. The good thing is, as I mentioned, is the online-offline consistency. Basically, you just expand your single node prediction to many, and every node is doing what it's doing for like online. So prediction on each of the actor basically. You handle your own way to model download, data download. You can do some sharing or not sharing. You run your individual inference server, for example, vLLM. This basically we use it for text generation. Then we can also use a Triton server like for handle statistical like embedding. The inference server, they provide a different type of API. For example, vLLM provide a nice like imprecise API for the batch prediction. So basically you can work like a function call, like a batch prediction, batch in, batch out. You get it. It's very easy for integration. But a lot of server nowadays they provide like a separate process, either as a separate process or is you can use a sidecar in a container, then use the HTTP or gRPC client to make the prediction either synchronized or async. So the way you run it, you start a server, start a client, use a client, send a request, and get the result back. You can shut down the server. For Triton, we use it this way. Since for offline, we also basically mimic this process for online. vLLM also provides such API, but since they have those convenient API, so we use it this way. Another thing to mention, the GPU parallelism, because you need to handle multi-GPU. There's many open source solutions that can handle this nicely. For example, like DeepSpeed. DeepSpeed, usually people use it for training, but you can also use it for inference. But inference at some point is an easier case for training. Then you can use MPI multi-process. This TensorRT-LM actually used this way. Another way is using Ray. Using Ray, actually, the vLLM actually have a way to use Ray to manage the multi-GPU on the node. The next we're gonna mostly talk about how we leverage vLLM and Array to actually implement it's a basically efficient batch prediction, also save a lot of code. For vLLM, basically, is you probably already familiar with in the past presentation. It's efficient, scalable batch prediction inference. It provides a high throughput, is effective batching, KV cache. It has a page attention for the memory. To efficient map the memory to reduce the memory fragmentation. It's scalable, it's handled the multi-GPU inference pretty well, it's pretty easy and convenient, and it has a wide spectrum model support. So basically, here are showing the API. Basically, it's a simple in-process batch prediction API. Then it's very easy to load the model. You can download the model base from Hugging Face and just point the path to it. Then you can load the model. And for the tensor parallel, is have a simple configuration. Just specify the tensor parallel size and tell how many GPU you need to use. You're going to find GPU and load the model. It's pretty efficient. It's for memory-wise everything. Then you can use this simple API to, for example, the text generation. So, so for the batch prediction, the read data actually is pretty convenient to use. It has a streaming execution with read data, and they have concurrent reading, prediction, and writing. So you can use a map batch API. Basically, you can pass a vLLM as like a predictor running on each reactor. Then you can pass the configuration of a model pass, how many GPU you need, and those text generation parameter like temperature, top P, max token as an argument. You can pass through, then going to pass through this predictor in each reactor. Then you can use this concurrency to control like how many actors you need. For example, you run 10 or 20, based on your job size. The batch size you can specify when the streaming is going to basically split your data into chunks to pass up the reactor. They also let you to set a resource. Resource can be to actually set your scheduling policy. So you want to, but we use a stricter pack. I think this consumption vLLM prefer. So basically, you can pack your actors among each of those nodes you actually specified. So here we show the we maybe call it optimized implementation, because compared to the original application, all optimized for batch prediction. So instead of in the previous implementation, we actually claim the node with the necessary resources. For example, we need 2 GPU, we claim the 2 GPU on each node. But then here the case, we basically claim the whole node. For example, if you have 4 GPU, claim all the 4 of them. If you have 8, we claim 8 of them. So the reason we do this is to avoid the GPU fragmentation, because a lot of times the batch prediction, you share the pool with the training pool. For training, a lot of times they want the whole node because they need more GPU and more resources. If we use a batch prediction, we claim the partial of GPU, the problem is won't be able to use the rest of resource for training. So this way we claim the whole node, then but we split into different groups with the reactors to claim the number of GPU is needed. For example, it's a mixture. You need 2 GPU, we just put 2 GPU on each of the actor. This is pretty easy to specify, and earlier you can set up the tensor parallel, how many GPU they need. They're going to actually locate the number of GPU for you. For the data downloading, because the previous implementation, we download the data for each of the reactor, but here we download only the read and use the streaming to actually stream to each of the reactor. For the model, basically, we used to download the model for every actor, so each got each copy. But since I mentioned for the model, since a large size, so one is take resources, another is also when you download, for example, you have many of them, you can download concurrently, you're going to pose like network pressure to your system. So basically here we download the model basically in on the same node, we download 1 copy. So if you have a GPU, you're going to share all those models 1 copy. So you can reduce your the model download actually pressure. So the way it works, the data download to reworker, streaming into so each of the actors. Then you can aggregate to the head, then upload to HDFS. So that's basically this implementation basically compared to this code implementation. That's how it works. So here we show some the benchmarker result. So This is basically shows the batch size and the number of tokens for the throughput. So you see with a larger batch size, you can see the overall throughput can increase, but in general flatten somewhere about like batch size like 64. For the mixture 8x7B model, we have 50 input. We can get somewhere about 500 tokens per second per GPU. So our typical job, we need to handle like 50 million rows, and the output token usually won't be this many, this 100 or less. So for this job, we found we can use somewhere about 80 H100, so we can finish the job in less than a day. So typically, this meaning we are able to support our application for a daily job. That's the original problem we are trying to tackle. So we can expand this to more, but we only couple hundred GPU we can use. So we usually don't use all of them. We can spend. Also, we found that you can actually, it's easier to you can split your data into a smaller chunk. So you use our orchestration pipeline to handle them in batch, rather than basically do a large, super large job. Because super large job, you can have run longer time. You have run into higher chance to fail, because you distributed. If you have a certain fill rate on one of the actors, you have so many, and with the time you get accumulate a good chance to actually fail. So next we're gonna need to implement like a better fault tolerance. So that's something we haven't implemented. That's something we're gonna do next, so we can make the job more robust. So basically, summarize what we're doing. The challenge basically, you're gonna have the resource pressure, so you need to handle because super large size, everything. Either the model saving pressure, also the bandwidth pressure. The low throughput, basically, you basically need to have like effective batching. You need to basically lower your cost. So the GPU orchestration, you need to handle basically node-wise. You can also handle basically in node. You also a lot of time you handle the online-offline consistency. So I can talk a little bit more here, because a lot of our big application we have both. When the online is on, we want the offline to be on. So we try to make them consistent. But some of the job basically we only have offline, so we can optimize offline. But if you have online both, you probably need to got a trade-off like your efficiency and so the online-offline consistent. You don't want to, one is the result consistency, or another is you're able to easily enable the offline if you have the online potential already. So we use the original application to scale to many, so we can quickly got offline application ready. But for those, I mean, basically with Ray and vLLM, we basically makes the batch prediction job easier. You use Ray, you can help you easily scale your job. You use vLLMs, you have an easy and efficient batch prediction applications. Yeah, that's pretty much it. So I can answer some questions, or you can reach out to us if you have anything to discuss. Yeah.
If anyone has. Hello. I probably missed the reason, but why you want to use Ray head node to download the data instead of Ray? Because it might crash the head node easily, right?
You mean here?
Yeah, here.
Oh, this I think this model Ray database. You only need, because in the earlier we download the data from each of the actors. In this implementation, you download from Ray head, and your data can do the streaming to each vector. These are more like the Ray data generation. So we can maybe try other way, but so far it works fine. I mean, so as I mentioned here, so you can you can have a super large job. I mean, you download a lot of data and process in 1 hour, but you can also try to split it into a smaller chunk. So basically, you have one field, you lost a few hours job most, then you can basically maybe redo it. So this way, you don't lose everything. So the risk so far, it looks fine for us. Yeah, I think it is a concern, but so far it's still okay. Yeah.
And maybe you need to learn more about the ray data. That's another library, ray data in the head node.
Yeah, you need to install the ray data. Yeah, have a ray data library, right?
So I don't know if you covered this in your talk, but for your batch predictions, are you sharing prompts, or they're all different prompts for each row?
Share prompt?
Yeah.
I'm not sure what you mean, the share prompt. So
you can have the same prompt, but different input to do the predictions.
Oh, no, we do not. Usually the prompt engineer is done before coming to the prediction. So that's a good idea, but yeah, right now we're not doing that yet. Yeah.
Okay, and maybe this is a more vLLM question. You said you do a pack strategy, strict pack.
Mm-hmm.
So just curious what the other options are and trade-off with the.
So I think there's something we developed the VM developer. I think we have them here. They can answer maybe. Basically, after I think vLLM v 0.26, they kind of asked to restrict it pack to make it work. So I think recently the newest, because my reason I think is they use array underneath to manage multiple GPU. I think I talked with them, they're saying they're switching to use a multi-process to handle it. They don't have this problem anymore. But that's kind of one of the reasons we use a strict pack. Yeah.
Also, like the strict pack should make sure the process group does not span across nodes. So if you have tensor parallel, then inside one node, the communication is more efficient.
Thank you for the presentation. My question about, you mentioned that you used a cluster with 80 GPUs.
Mm-hmm.
Do you have a number of reasonable size of cluster for this kind of methods? Like for 8, it's not enough for parallelization, or
we don't have that exact number because the H100 is pretty expensive resources. It's we use a lot of for the training, so we can only use a part of the resource for the scoring, so we cannot use all of them. Also, the goal is for us to finish. We want to do it daily, so finish in a day. 10 to 20 hours, and the amount of data we need to handle about 50 million. We just found that 80 GPU is enough for us. We should be able to spend. We just didn't actually test, but basically the refocus, they're saying for theirs they do like a lot more with no problem. But for us, we don't have so many GPU for us to test, and we don't really need it for our job. But I think you can do a couple hundred. It should be okay.
I mean that if I have a cluster with 8 H100 GPUs, is it reasonable to use the same approach as you presented?
Depends. I mean, for this approach, we can claim the whole node 8 GPU. But that's also if some cases I mentioned, sometimes we want online-offline consistency. Depends on how the people implement their model like how many GPUs you need. Sometimes we want to mimic what their people doing on a single node for online. We not going to claim all the GPU resources. So this way, probably not the most efficient way to use the resource get the best, but sometimes the job size is not so large. We just want to easily bring up the batch prediction. We don't have to claim all the resources. We just do the same as online. So, but we found if this is a real big job we optimize, we'll probably optimize for the batch. One of the challenges is hard to optimize for both, for the online single prediction and the batch prediction. So, yeah. Oh, sorry, my timer. Any other questions?
Sorry, I had just two quick questions. So for the first one, you mentioned that there is some issue with co-locating the inferencing with the training together on the same GPU. Could you kind of elaborate on that? I thought you have like resource allocation to provide this isolation. So what's the missing part?
So basically, for training, for example, like A100, we have 4 A100 on it. Often they do, like for example, they want fine-tune a 70B model. They need the whole full GPU, the whole node. So if we do the scoring, we use like 1 or 2 of GPU from that node. We leave like 2 to 3 of the rest of them. But when the training job, they try to claim full GPU, they cannot find a node to do that. That's a fragmentation I mentioned. But recently, we also trying to do the scheduling a different way. For example, the bin pack, we can pack our scoring job. You claim 1 GPU, we try to pack them on the same node. Then you basically still, although you're not claiming all the GPUs, but can still able to fully utilize 1 GPU, not expand to many of the nodes. That's another way to solve the problem. Yeah.
Gotcha, thank you. The second quick question is the batch size experiment that you guys did. So we saw that it's saturated on the larger batch size. Was there any other things that you found with like having a larger batch size? Is there any downside with that, or any other things that you guys tuned for the workload?
Because the mixture model, this size is we often use for fine tuning. For this one, we don't see a problem. But I think if you go to, for example, the Llama 3, they have a pretty long text window. So basically, your batch size longer, you may not have enough memory to handle it. So you probably have to tune your batch size down. Like for the KV cache, like for 5B model example, you already you use 8 GPU to host it. You're going to have latent memory of KV cache. If you increase the batch size, you can probably run into a problem. You need to basically reduce your batch size. That's one thing I can think. Hopefully answer your question.
Okay, if there's no more questions, thanks for the talk.
All right, thank you. Thanks for coming, everybody.